And if it's just that's fine.
That's a large part.
I'll start whenever you think YouTube is. Okay, cool. Okay, so can everyone in the back hear me? Let's start there. See, 1 thumbs up, 2 thumbs, great. Okay, so welcome. Steph Henderson couldn't make it today at the very last moment, so I get the privilege of announcing and introducing the speaker for the first colloquium in person that we've had since March 2020. Let's give that a round of applause. Since this is the first colloquium in a very long while, I'm going to go through a couple of the logistics just to make sure we're all on the same page and for the folks who are watching at home on YouTube. So this semester's colloquia are going to be a mix of in-person and online. As you can see, this one is an in-person colloquium. Because we will also have international speakers, and those will always be a virtual seminar, make sure to watch for what the time of day the colloquium might be at. Given we have some speakers, I think, in Australia and Asia and Europe, so the colloquium might switch around in time, so just be aware of that. All colloquium are going to be both in-person and virtual, and they're being streamed on YouTube. So as a courtesy to others, please do not come to colloquium in person if you are sick with anything really, or if you think you may have been exposed to COVID, as a courtesy to everyone else here. You can easily watch online from home, you can ask questions in the chat, and when we get to the question part of the colloquium, Pete will be bringing those up to questions here. So as just a general reminder, during that Q&A session at the end, let's keep our conversations respectful, and don't be afraid to ask questions. If you're confused, it's likely that someone else is, and often the simplest sounding questions are actually getting at something that's quite fundamental, so be brave, it's okay. And I'm going to, at the very end, if there's any student questions, I'll preferentially select those first. So, without further ado, today's speaker is our very own Matt Hitchman. Matt received his PhD from one of the other UWs, that's Washington, not Wyoming. In 1985, he was working with Conway Leovy, using results from the LIMS instrument to study wave mean flow interactions in the stratosphere, a theme that he has been working on ever since. So he started here in 1988. He was the department chair from 96 to 99. He teaches a variety of courses, 171, 405, 610, 705. Everyone, I think, pretty much everyone's had a course with him who's here. He's published a ton of papers on a variety of topics, including mesoscale and synoptic scale dynamics in the upper troposphere and lower stratosphere. Last year he was on sabbatical in Japan. He taught a global change class while he was there, and it was the first ever English course that Kyoto University had. While he was also there, he did some research and work on the topic of today's colloquium, which is an observational history of the direct influence of the stratosphere QBO, that's quasi-biennial oscillation, on the tropical stratosphere, upper troposphere, lower stratosphere. So without further ado, I'll hand over to Matt.
Thank you. Just that class in Japan, they listened to my Japanese and said, you're going to have to teach this thing. Sumimasen. Okay, so this title is long, but if we unpack it, you'll see that it makes sense, and it's almost required in order to describe the scope of what I'm working on. So it's an observational history, and I will touch on modeling and theoretical ideas, but this is really focusing on observations. And it's about the direct influence of the QBO. And by that I mean, when QBO wind regimes get down to the tropical tropopause region, these meridional circulation cells extend from the tropics out to the mid-latitudes. And so there's a kind of a unified antiphased response in the tropopause layer. When a QBO wind regime descends, you'll have, say, QBO westerlies descending, you'll get a warm anomaly at the tropical tropopause and cool anomalies in the subtropical tropopause regions. So that's what I'm calling the direct influence of the stratosphere QBO. During this history, you'll see what the QBO is. We'll define that. And I'm also concentrating on the tropical and subtropical upper troposphere and lower stratosphere. That sounds long. And the tropical transition layer is embedded in the upper troposphere and lower stratosphere. I think of the UTLS as thicker than that, encompassing the TTL. And so that's why I describe it this way, because these thermal anomalies are fat. They're 5 kilometers thick and thousands of kilometers wide. So if you pick say, 100 hectopascal temperature, or if you pick cold point tropopause temperature, or if you pick the elapse rate tropopause, these are all about a kilometer apart, but they fit within the anomaly, so it doesn't really matter. And I'll show you in 3 different data sets if that's the case. And so tropical and subtropical, that's a direct acknowledgement of the integrative factor of this QBO mean meridional circulation cells, which were only theorized. And finally, in numerical models, we've been able to eke out long-term averages of W and V and actually quantify mean meridional circulation associated with the QBO in global analyses for the first time. So this quest began, for me, I'd say in the early 90s, when Chip Trepke came here to work on a PhD with me, he introduced me to aerosol climatology, just the idea of volcanic aerosols, and so he and I studied that, and he was interested in the QBO modulating the tropopause as one of his research interests. And I also, in the mid-90s, started talking with Chris Collmore, who came from CSU, where there's a fine tradition with Bill Gray of trying to investigate what we now call the direct effect of the QBO on things like rainfall, winds, and hurricanes in the tropics and subtropics. So it has a kind of a long tradition. And around the year 2000, I tried to publish a paper. It didn't work out, but finally I did just last spring. So that's good closure for me. But the process was interesting. Within SPARC, which is the study of the stratospheric and tropospheric processes in the rolling climate, we established this initiative, which we call SATIO TCS, and here's the logo I designed to show, based on Trepke and Collmore's diagram of the QBO modulating tropopause, that may influence, and you might have a nonlinear feedback between QBO easterlies elevating the tropopause in the deep tropics, and somehow some nonlinear feedback with convection, so the QBO signal is amplified where there is convection. That's a good new research question for people who study tropical cloud dynamics, is in order to, can you explain why that's so? I have just a few notions, but I think it's a good thing to consider if you have an interest in that. So I'm glad to say that this was finally published in a pair of papers, and Peter Haynes, he took on the role of describing all the theory and modeling work that is related to this direct effect. And I'm glad Peter's on board, because I'd say 20 years ago, he was very much in the camp of extratropical stratospheric dynamicists, which they all think, and many of them still do, that the tropics are completely passive, that whatever happens at the tropopause layer is controlled by extraplanetary wave drag in the winter side. It's called the downward control theory. It goes a little too far. There are legitimate things that are inherent in the tropics, such as the QBO, that are useful to consider as somewhat separate entities. Well, our understanding of the stratospheric circulation in the tropics began with the eruption of Krakatoa, and many of you know this story, but it's fun, so it's worthwhile to relate it again. This is just a wood cutting from, 1680, and it shows Krakatoa erupting and ships trading back and forth between China and India and the rest of the world. It's a very popular trade route through this strait, which happens to be over here between Sumatra and Java. When I was young, a movie came out called Krakatoa East of Java. That was the title of the movie. No, I'm not a producer, but I do observe geographically that Java is actually east of Krakatoa. But maybe they have something in mind intuitively. I'll show you what happened with the eruption. Oh, just a comment about Wallace. Alfred Russel Wallace, not only did he, by 1863, understand a fantastic amount about natural selection and co-wrote with Darwin at this, piece that they introduced in the Royal Society, but he stayed in this region documenting some 300,000 species of beetles or so, and birds and stuff. He has really interesting paragraphs that presaged the theory of continental drift. He said these two pieces of land came together somehow, and he didn't know how. It's pretty interesting. Okay, back to the eruption. It was August 27th in 1883. It was in the morning. I guess in horror films it happens at 3:16. At 9:15, Mount St. Helens blew up in the morning. It was about that time for Krakatoa. There really isn't a 24-hour preference, probably, but just a coincidence. Anyway, the The tidal waves, I think, killed 35,000 people, and it pushed this boat up the Coropan River, the ship Barrow, like 2 miles up the river. And it doesn't exist if you went there anymore. People stripped all the metal off for scrap metal. But there was a Captain Thompson on the British ship Medea who saw these waves coming and got out a sextant. Wow, there's this huge plume. So he gauged that the top of the plume was some 16 miles. So that's getting up, toward 30 kilometers, well into the stratosphere. So we know the stuff got into the stratosphere. But not only that, you can tell if there's a volcanic eruption if you see really beautiful orange sunsets. This is a picture by Alan Robach after the El Chichon eruption, and this is May 83 looking from, I think, the capital west over Lake Mendota. Well, you all know how that works. A spectrum of light comes from the sun, and blue light is scattered more effectively by sulfuric acid droplets that are 0.1 to 1 micron in size, and the red goes forward, so at sunset you can see the orange and red color. Well, in the 1800s it was said that the sun never sets on the British Empire. They had all these territories, right? And so people would keep diaries, and it was popular like barometers. People liked to take meteorological observations back then. And so they could map out the isochrones of arrival of this cloud, and lo and behold, here this is 10 days after the eruption, September. There's the point of eruption. The leading edge of it hadn't quite wrapped around yet, but it did come from the east. So in a sense, Krakatoa was east of Java. Right? The movie director was right after. And then, what's this, November 30th? This is yet another puzzle. So after a large volcanic eruption in the tropics, and also extratropical ones, stuff will get in the tropics. Within a few months, you have a pretty robust set of sulfuric acid droplets, and it'll be arranged in a ribbon shape with pretty strong gradients in the subtropics. I think maybe this mixing has to do with mixed rotary gravity waves, actually. They're wave number 4 and 5, and they kind of stir and mix within the tropics. That gradient at the edge is not very well understood. Some people think there's a PV gradient there, but it's in fact the maximum in wind shear, which means that it's in quadrature with the PV gradient. It takes a while for material to get into the mid-latitudes, and everywhere in the mid-latitudes, the isochrones of arrival of the volcanic aerosol in the stratosphere came from the west, and that's because you need to wait until wintertime for planetary waves in the winter side to get going and dip into the tropics and strip material out, usually in anticyclonic Rossby wave breaking patterns. So they knew that there was pretty strong easterlies. I guess if this is 10 days, you'd have to go at 30 meters per second or so to do that. And that is about how fast the easterlies in the QBO are at the maximum, is minus 30 meters per second. So the picture that people had for after this was, oh, we didn't know what it was, but in the stratosphere over the tropics, we have easterlies, and we call them Krakatoa easterlies. That was just the way people referred to it. And then came this interesting set of observations by Arthur Burson, and I'd like to thank Stefan Hasternath for giving me this once upon a time. I was able to use my 3 years of high school German. This is the report of the aerological expedition, the King's aeronautical observations to East Africa in the year 1908. And in 1910, you could buy it for 10 marks, this report. So this is at Shirati, 1 south, 30 east, and it's August. So this is, I will show later, I'll try to remember to tie it in with an observational plot. Well, I could go pick up the globe, but you remember that in the northern summer there's a monsoon, and at the top of the troposphere there's a big gyre, a Rossby gyre, and it circulates around, and the flow in the tropics is from the east, very pronouncedly, into Africa. So if you go up in altitude, say, here's the wind direction. This German nomenclature, well, let's go up to 15, 16 kilometers. North 78 east and south 86 east. Those are both easterly flow with a peak at around 16 kilometers, 34 meters per second easterly. That is the core of the equatorial flank of the Tibetan High. But the curious thing was that when the balloon ascended, it got into this little thin layer of westerlies in the 18 to 19 kilometer layer, and then the balloon Einballung get lost. And the balloon broke and it descended. 20 kilometers is a pretty good altitude. These are very high-quality radiosondes. Now, the problem is tracking them over the horizon. Sometimes the winds are fast enough you couldn't track them much higher, but in this case, the balloon broke. Even now, people are just trying to expand the technology of balloons. Takanari Kinoshita was just visiting here, and he and his colleagues in Japan had these 3-kilogram balloons that can get up to 40 kilometers altitude. And I think there's some experimental balloons in Europe that people have been using as well. Okay, so then the picture that emerged after that was a thick layer of easterlies in the stratosphere, tropics, overlaying a thin layer of westerlies traveling the other way. So it's like that. And I don't know if you've ever been in Japan, you have those race courses of sushi, one going this way, one going that way. It's kind of like the early view of the QBO. And then, astonishingly, Richard Reed and his co-workers, also Verriard and Ebden in Germany at the same time, discovered by processing radiosonde data, these are monthly means, they found that these wind regimes aren't static. Here's an easterly wind regime. It's pretty thick. Like if you measure at this point in time, you'd have a thin layer of bursts and westerlies and a thick layer of Krakatoa easterlies, but they're not steady. These regimes descend with time with a periodicity of 24 to 32 months, which is extremely intriguing to many people. People in the physics department, they just think this is really interesting. It's not an annually cycle, there's no annual cycle driving here, nothing like that at all. So it's kind of an interesting thing how this goes. It's just a wave mean flow interaction problem. I think quantitatively, perhaps 30% of the westerly phase is Kelvin wave absorption. The rest is the whole spectrum of gravity waves that have westerly phase speeds. And then the easterly flow is maybe 10% mixed Rossby gravity waves, and the rest of that is easterly gravity waves across the whole spectrum from minutes to hours for their periods. They're all created by thunderstorms in the tropics and subtropics punching into the bottom of the stratosphere. So if you hit a drum head, there'll be natural modes of vibration. Gravity waves radiate up in a fan-like pattern seen from the side, or concentric rings seen from the top. And the energy goes up. When waves get to the level about where the winds are traveling as fast as their phase speeds, there's an infinite amount of time for them to be absorbed. And so the group velocity goes to 0, the vertical wave number goes to infinity, and they get absorbed by as yet unspecified processes involving turbulence and radiation. So let's take a westerly case. Gravity waves are being absorbed here. You speed up the flow in a westerly sense. Let's say that's toward the east and here's the equator to the right. You're going to go up the pressure gradient. So that implies a convergence into the tropics if you have westerly wave craft. And that implies a meridional circulation. The opposite happens in easterly shear. Two more points before leaving this wonderful picture. A lot of people use 30 hectopascals as an index for the QBO wind. And that works pretty well for what's called the Fulton-Tan effect, which is how do planetary waves refracting in from higher latitudes in the winter interact with the subtropical zero wind line, which is farther poleward during QBO easterlies. In that case, yes, it's not a bad thing. But if you want to study the descent of these wind regimes into the troposphere, where you have variable penetration of deep conduction into this lowest layer, I mean, the tropopause is 80 to 90 hectopascals. These wind regimes descend through the Utls, somewhat into the troposphere. Well, if there's a direct effect on the troposphere, modulating convective cloud tops in some fashion for these wind regimes, or the associated temperature anomalies, then it's better to use a 50 hectopascal index than 30, or even better yet, this 50 to 70 hectopascal wind difference, which is what Hitchman and I used in 2001. The reason why I say that is, let's just take an example. All right, here's minus 20 meters per second at 30 hectopascals. At the same time, it's plus 5 meters per second at 50. So they're not precisely uncorrelated. People often say, oh, well, 30 hectopascals is a really good proxy for the opposite phase of the QBO if you keep on 50. That's not quite right. you have all sorts of difficulties here. There's timing westerlies here, timing easterlies here. Westerlies tend to descend at a different rate than easterlies. And there's variability from year to year due to ENSO and all sorts of other things, such as extratropical planetary wave timing. So the relationship between, the correlation between 30 and 50 isn't -1. Put it that way. And this just shows the QBO goes on and on. We think it has gone on forever. Except, the year 2015, 2016, never happened before, maybe never again, a thin, weak layer of QBO westerlies was descending, and there was such a pronounced Rossby wave breaking event coming into the subtropics, and stationary Rossby waves slow westerly flow down when they get absorbed. It wiped out the QBO westerlies. It was astonishing. Never happened before. So that's a clue that there is a little bit of wave drag associated with Rossby waves coming in from the side that need to be accounted for. And it sort of confirms, I think Tim Duncan in '83 wrote a paper about that, and Jonathan Kinnersley is also keen on that idea. Yet another idea that was sort of subsumed by the steamroller of the majority, in fact. But now it's come out really loud and strong that it's not entirely tropical waves excited by convection. There are also synoptic waves in the UTLS and mid-latitude planetary waves in the stratosphere that can affect the QBO and interact with it. All right, so just to distinguish these two effects, the stratospheric pathway is the Holden-Tan effect. This very nice woman showed up from Korea when I was in graduate school, and she did this study and then went home. I don't know what happened to her, but it was great. She just was smiling and reported this, became extremely famous. The idea is that, well, I mentioned, the QBO structure in the tropics will modify how planetary waves in the extratropical winter refract. And instead of getting all the way into the tropics and meeting there and being absorbed there, they tend to get absorbed in mid-latitudes. And you could think of a sudden warming as being more likely during QBO easterly. There's a smaller volume of westerlies to stop and reverse direction. You could think of it that way. So QBO easterlies involve a disturbed polar vortex. QBO westerly is stronger, deeper, colder vortex. Instead, I was interested in the direct pathway because there's a really fine literature beginning in the 60s, 70s, 80s that talked a lot about the effects of QBO regimes in the lowest stratosphere affecting different things like cyclones, tropical cyclones. So the idea is that maybe the QBO can directly affect the tropical, subtropical UTS, and the integrating concept here is the mean meridional circulation has a finite span, and so whatever happens in the tropics must happen in the tropics and subtropics at the same time. So other authors, I could look them up for you, have discussed patterns of temperature, height, clouds, rainfall, wind shear, tropical cyclones, subtropical jets, and subtropical Rossby wave breaking. This is a pretty robust development, but it was largely by people who studied things like tropical radiosondes, and people who were studying extratropical preeminent classical, theory. They just took a different point of view. And I went to a meeting once where we were supposed to talk about these things, and I gave a talk on this. There were 400 people there. I think all the talks were on the Holden-Tan effect. And I had the only one talking about modulating tropical convection, and I was really grateful that I took some flack over the years, from 2000 to 2005, giving talks. But I must say, Tim Dunkerton and Mike Wallace both came up to me and said, keep working on this, you're on the right track, this is really fascinating. So, thank you. Sometimes the majority, like if one theoretician puts something in place that's useful, and then a whole bunch of people who don't quite understand all the limitations view it narrowly and build up an inverted pyramid, that whole thing can fall. All right, so in this work, we're focusing on the historical overview and then the modulation of UTLS synoptic structures. This was particularly resisted because the whole idea is that the QBO is zonally symmetric. So when Amihan and Hitchman and I found in around 2000 that there were significant geographical variations of the QBO temperature signal in the tropics. Nobody liked that. It's wrong. It's completely a data problem. I'm glad that turned out to not be true. So here's the sequential development of the observational capability. We have Reed et al. And Berrier and Epton early on. So maybe this should be 1955 radiosondes onward. And there was a simultaneous development of the theory of the QBO and the medium meridional circulation that must exist. In the mid-60s at MIT, there was Leobi and Holton and Wallace and a few other people who were thinking about this problem. And Bob Dickinson, I think, may have come up with the first diagram of the mean meridional circulation as a guess. I'll show you that in a minute. The second phase of increasing observational capability was the launch of satellites. And I'll show you some zonal mean cross-sections from LIMS temperatures and SAGE and SAM2 aerosol, which support kind of a snapshot view of mean meridional circulation of the QBO. You know, you can't put an anemometer in and measure 20 centimeter meridional flow or 0.1 millimeter vertical motion. That just doesn't work. So, well, we'll get into that story. The third phase is the rise of global analyses. And from 94 to 2000, there were a few papers trying to look into the QBO effect on the zonal mean UTLS. And then finally, 2001 to the present, the last 20 years, people have, especially in the last 5 years, really come on board and trying to investigate further the seasonal and geographical variation of the QBO effect. You know, why would there be a geographical variation if the QBO is zonally symmetric? All right, so digging into the archives, this is 50 hectopascal temperature for different stations, Canton Island at 3 south. This range is more like 3 degrees, but let's call it 2. This is QBO westerly warm, easterly cool, westerly warm, easterly cool. So this fits with nominal theory. In fact, this is before any theory. So there was a quasi-biennial oscillation in the 50 hectopascal temperature, which is in the lowest stratosphere at Canton Island. Not only that, there tended to be an antiphasing in the subtropics here, cool and warm, warm and cool. It's not perfect, but there's a suggestion of that. So here's Dickinson's schematic from 1968. He said there should be some meridional extent to this, because if you want to have an easterly wind regime, you better have a cold anomaly under it, or else you won't satisfy the thermal wind law, which is good to better than 0.1% at the equator. F gets small, but it's a 40,000 kilometer scale. So what you have to have is rising motion to create a cold anomaly, but that implies sinking motion in the warm anomaly here. So the basic idea of how the warm anomaly's vertical motion field and temperature field fits in was correct. He made some guesses about the dynamics. With that term there, the convergence of meridional momentum flux, that's what happened in 2015 that wiped out the QBO westerlies. But most of the heavy lifting, the creation of the descending wind regimes is due to vertically propagating gravity waves excited by convection. So that's not really in that picture. And then we have perhaps the most famous description of this mean meridional circulation. It's by Plum and Dell. But I really do need to read the caption out loud. So I thought in this historical method I would just simply state in quotes what their captions were. And their caption says, this is a schematic representation of the mean meridional circulation driven by an equatorial thermal anomaly and the consequent acceleration of the mean zonal wind. Well, I don't know why he wrote it that way. He knew very well that, he parameterized in his own paper wave drag, and that's the whole start of the thing. So what you have to have is a patch of wave drag somewhere. So let's say you have a patch of wave drag here, and it's westerly up here. That will cause a convergence, a flow up the isobars, and that requires descent. So this anomaly, this thermal anomaly, should be regarded as a passive response to wave driving instead of causing the wind regimes. Well, you'll notice something else here. There's no vertical scale here or here. So the question was, how far into the mid-latitudes does this extend, or does it not at all? Is it purely a tropical phenomenon? How narrow are these return circulations on the flanks of, say, descending warm QBO westerly regime with the rising motion on the flanks? How far away is that? And is it tiny? Does it come up? Is there rising motion everywhere on the planet to compensate the sinking in the tropics? Or is it concentrated? People didn't know. There weren't observations to answer that question. A couple more pieces of information. This is re-engaged, 1985. These are all Micronesian stations, but you can compare with ones around other parts of the tropics, like Wake and Ascension Islanders in the Atlantic. You can see these blue lines are every 2 years, so that's biennial. But what you can see with these arrows is that there's a quasi-biennial variability in the tropopause altitude. And this variation is on the order of 300 meters. Let's call it the range instead of the amplitude. And from delta P is minus rho GdZ, since density is 0.1 or so kilogram per cubic meter at 100 millibars, then since gravity is 10, then 300 meters is 300 pascals, or 3 hectopascals. So the pressure goes up 3 hectopascals in the tropics during QBO westerly. It's lower down altitude, 300 meters lower down. At the same time, in the subtropics, the tropopause is 300 meters higher up. What might this do to convective systems? You know, if you have a thunderstorm that punches into the bottom of the stratosphere, let's let it go a little farther, maybe another 300 meters. Could that accelerate the storm somehow? That's the question for somebody to answer. I don't know enough about it. Here comes another really interesting thing, which I remember it gave Holden apoplexy. He says, no, that's impossible. But it's turning out to be actually true. So this is Yasunari in 1989. Here's a QBO periodicity at 50. This is the coherence between winds at 50 and 700. And if you plot the power, so this is U squared, then this peak at 50 hectopascals, 80, the square root of that, 9 meter per second amplitude. This, what, times 1, 3, square root of that is 1.8 or something. So this signal is about 4 times bigger than that, which isn't that bad for 700 millibars. And what it says, he says, during QBO westerly, the Walker circulation is diminished. And people said, no, you can't conclude that. But other people who have found similar results, including people who work at CSU, so it's emerged to be actually probably correct. And during QBO easterly, you have a lot more thunderstorms in Indonesia. The Walker circulation is more robust. So, Yasunari was right. Here's another attempt to try to make some sense of how far poleward do these meridional circulation cells extend. This is LIMS temperature, zone mean, and this is potential temperature, rather. No, temperature. And what you can see is a spreading out of contours here and a pinching here. So I just put in some arrows that might be compatible with that pattern. This happens to be right here in the westerly regime. This is centered at the easterly, maximum easterly level, where you have a drift down across isobars and therefore rising motion and cooling. And then with the thermal wind law, you get easterly shear. I also plotted our scale 2D, and you can see maybe even better evidence of deformation of poleward spreading at the level of maximum easterlies. And return circulation, suggesting that this might happen around 20 north, 20 south. Didn't know. Just a guess. Here's another view in aerosol. This is sort of that tropical regime that I mentioned where the volcanic aerosol tends to reside. And this snapshot is for a period of time of westerly descending over easterly, and the sage instrument would raster across the latitudes, and you could get a 30-day image. And you can see this characteristic horns of high aerosol amount coming out of the tropical reservoir in the return circulation, and a descent of lower valleys of aerosol underneath the westerly maximum. And then the reverse was observed for QBO easterly. And if you bin all that data together, QBO westerly minus easterly, there's a 20 or 40% difference with more aerosol in the subtropics, lower stratosphere during westerly, more aerosol in the tropics during QBO easterly. That type of, this pattern has also been confirmed by people like Choi, who studied methane, and other stratospheric tracers that they find similar modulation by the QBO. Well, that's not the tropopause yet, though, is it? So let's talk about this one. This one has become, I think, pretty famous. It's similar to diagrams in Gray et al. And Chip Trepty's PhD, but I think Chris did a better job of introducing this tropopause here in such a way that it really was evocative of, darn it, maybe it's true that these QBO wind regimes actually modulate the UTLS. And here's George Reed's very fine attempt to, with theory and prudent thought, to take observations and calculate the temperature anomalies that have to exist in order to explain the observed QBO winds. And he thought, well, maybe it's about a 3 Kelvin range in the tropics and in the subtropics, antiphased, and he guessed that the scale was about 30 degrees of latitude. Turned out to be overestimating this amplitude by maybe 30%, but the meridional breadth is similar to what we find in modern observations. And then Bill Randall was interested in this problem too, and he showed that the tropopause, if you have warm tropopause in the tropics, then you'll have cold tropopause at around 25, maybe 30 degrees. Don't know what happens outside of there. There was kind of a prohibition in thinking that QBO could really extend outside of the tropics at the time, so people didn't really investigate it. And also tropopause pressure. If you have a warm anomaly, the tropopause will be at a lower altitude and a higher pressure. About the same time, Hichman, who I think now still works in the physics department here, showed this QBO temperature anomaly, warm and westerly in the tropics with a node at around 15 to 20 degrees, and then at the opposite sign, perhaps extending well into the mid-latitudes, is what this figure says. If you look at the 50 to 70 hectopascal wind shear, this is interesting to me. It looks like there's no signal outside it, and you have a pretty good signal in the tropics, and so it's tempting to say, well, here's the true confinement meridional age of QBO. It turns out that from this study, we can now see that right here is in a node for delta U for the QBO. I'll show you. You can only understand this if you look at the whole meridional, latitudinal, altitudinal distribution. And it turns out that QBO westerly at 50 is highly correlated with enhanced westerlies at 150 hectopascals in the subtropics. And it's a U-shaped structure in the zonal wind maxima. I'll show you that in a minute. So this is just a binning method, and you can do statistical significance with the student t-test. And so we color our maps that way. Here's just an example. This is northern winter and summer. In the climatological average here, we're closer to the sun. You get 7% more radiation. The extratropical wave drag is stronger in the northern hemisphere with its continentality. Tropopause temperatures are some 3 Kelvin warmer in the summer because of those reasons. I don't know which is the relative proportion for the explanation of that. I think that 7% variation in insulation's got to be worth something. This is QBO westerly minus easterly during December, January, February. You can see the convective centers, Amazonia, Africa, Indonesia in January, tending to drift up this way toward the Gulf of Panama and toward Southeast Asia in northern summer. QBO difference in temperature. Well, to first order, it is zonally symmetric. We have westerly QBO means warmer in the tropics with a node here. But at around 25 to 30 degrees latitude, there was a suggestion of a cool anomaly, the opposite sign. This is consistent with the meridional circulation idea. That's also true with June, July, August. There's a nice meridional stripe of warm flanked by cold. This is particularly surprising. The southern hemisphere winter has a statistically significant signal of the tropopause for temperature. That part was probably okay, but when we started to say, ooh, look at this, there's a big anomaly here over where there's a lot of clouds, and a pretty good anomaly over Africa, and well, I don't know about Amazonia, but there tends to be a correlation between the QBO range in temperature between westerly and easterly and regions of deep convection. Just kind of a general suggestion of that. We also looked at pressure, and here's the difference in pressure. QBO westerly, you have a lower altitude, higher pressure for the tropopause, flanked on the opposite sides by higher altitude, low pressure tropopause. Look at that significant raising of the tropopause in the southern subtropics during QBO westerly. Nobody studied this. It's wide open. How would that affect the propagation of waves in the roaring 40s and 50s, for example? Here's zonal wind shear. This spans the lowest stratosphere into the uppermost troposphere in the tropics. The 150 cuts through the jets and into the lower stratosphere in the next tropics. Well, you'd expect this to be positive, westerly minus easterly. This just shows, yeah, there's a QBO in the tropics, so that's good. More zonally uniform in this wind difference. But I want to point out, let's pick June, July, August. So the coloring is, this is easterly shear. So we're going upward from subtropical westerly jets into neutral flow. This is positive, so we're going upward from upper tropospheric easterlies into neutral flow, weak flow. So that's why that's positive. This really is, at 150 hectopascals, you have this jar, big easterlies at 150, but this is 70 minus 150. So going upward, you have an increase in wind from minus 25 to 0. So I just wanted to relay that because in a minute I'm going to talk about something that I'm interested in pursuing, which is the coincidence of the cloud convective centers, these easterly regimes, and the fact that both the temperature theory and the wind shear theory are geographically and seasonally similar, and you can't really distinguish the two. All right, so I wrote this up with Amihan and Chris Collmore and sent it to Jazz, March 2001. Two reviewers said, well, minor revision, just maybe change these few things. One reviewer said, well, I don't really understand if they've proven cause and effect quite, but let's go for a major revision. So we did those things, sent it back, had great figures, which you just saw, and with statistical significance. And lo and behold, the editor comes back and says, I'm going to override these reviewers. You have not proven this at all. And further, this quote's amazing, you are hitherto prohibited from submitting any material similar to this to any AMS journal. Have you ever gotten a letter like that? Kind of gets into you. So the next 5 years, I gave 5 talks on this, and people are going, oh, get out of here. But finally, I'd say the year 2010, Shigeo Yoden, a friend of mine, I was a postdoc with him in Seattle for a while. He's at Kyoto. He said, I'm interested in this. I think there's some legitimacy to it. And so he started to, within the Japanese government, come up with funding to look at it. And from 2015 to 2020, I gave another 5 talks associated with the Seikyo TCS meetings. And now it's starting to take off. In fact, I'd say 4 years ago, Suzanne Tegmar independently found some things in MER2 data. And Shigeo and Vinay Kumar, his postdoc from India, were looking into the ERA interim data. And that really helped make the argument. And their pictures support what I just showed you and amplify on things and really we're able to hone in and define new structures that we haven't seen before. So Yeah, now things are happy. People who study this is stratospheric and tropospheric influences on tropical convective systems. People who study the Holden-Tan effect, now they're coming to these workshops and they're interested in this topic. Yay! All right. So what did we do? We took, Amihan's data that she manipulated was NSEP data. We had two separate sections, 21 years from 58 to 78, 23 years from 78 to 2000. That's because we wanted to distinguish the effects of satellite data. That's a 44-year record. ERA interim, this is processed by Vinay Kumar, and that's a 40-year data set starting in 79. MERA-2 was calculated by Suzanne Tegmark, who's now at the University of Saskatchewan. It's a 30-year data set. I want to point out these differences. To define the QBO phases, we used 50 to 70 hectopascals on a wind shear. Vinay Kumar used the QBO first two EOF functions using a matrix of winds at 70, 50, 30, 20, and 10 hectopascals over the tropics. And you can do a clock with the first two EOFs in phase and have 8 quadrants. If you take phase 4 minus phase 8, it looks very similar to results from 50 to 70 wind shear index. And then Suzanne Tegmark, she wanted to use 50 alone. For some reason, kind of the QBO community is really focused on, they like 50 just by itself. Although I think 50 to 70 wind shear is a little better for looking at cloud top effects. Another difference between these data sets is we are looking at lapse rate tropopause, which isn't the same as 100 hectopascal temperature, or Suzanne used cold point tropopause temperature, wherever the temperature is coldest, not where the lapse rate fell below 2 K per kilometer. The altitude variation in these is about 1 kilometer, but again, this all works out, and it's a nice after-the-fact proof that these anomalies, by being fairly thick and fairly broad, it doesn't matter exactly where you draw a line through them to sample them. So here's the ERA interim results, which I think are nice. They're better than the NSEP results. This is 20 years of extra data, and it's got better statistical significance. And you can see the December, January, February. If we look at the contour interval, 0.51, this is about 1.75 to 2 maybe at the maximum. And again, a maximum in winter over, for the QBO range of westerly minus easterly, 100 hectopascal temperature, the maxima are over Amazonia, Africa, and Indonesia. March, April, May turned out to be a surprise. I didn't really pay too much attention to it in 2001. We had the calculations, and after the fact, I looked at it and, oh, it is similar to this. That's a pretty good signal. So here, without any dashed lines, that means this is statistically significant, and also here. So you can see the antiphasing, and we purposefully went all the way up to 40 north and south in order to be able to see this. June, July, August, things get a little more relaxed, but basically, it's similar in the zonal mean antiphasing between the subtropics and tropics, but less zonally asymmetric during these two seasons. Here's Suzanne's results with MERA-2 data. In the annual mean, you can see DGF and MAM contribute quite a bit. Well, they all do, but you can see these centers. Actually, March, April, May is interesting. There's a paper by Adrian Tuck in about 1990 that shows the coldest, highest tropopause in March, April, May is in Africa, not Indonesia. And then June, July, August, and SON are a little bit slack in this regard. Smaller amplitude QBO, let's say 0.5 Kelvin instead of 1.5. I thought it might be good to just take a sample and put them side by side. So this is, on the top was the original 2000 study, and here's ERA interim, and then there's MERA-2. Note that this stops at 20 degrees north, this is 40 north, and this is 45. So the patterns are really quite similar. This is just cut off right at in the node here. Cold point tropopause temperature range tends to be a little bigger, maybe 2 Kelvin at its maximum in Indonesia. And you might think, well, why care about 1 or 2 degrees Kelvin? I guess an example would be global warming. 1 degree is a pretty big deal. Somehow, it seems that 1 or 2 degrees Kelvin temperature anomaly near cloud tops has some subtle influence on cloud development. All right, so this is the last kind of new stuff, and I kind of want to work on this a little bit more. It shows QBO differences in zonal wind at 150 hectopascals. And yeah, you see in each plot, if you blur your eyes, this is westerly enhancement in the subtropics. And the lowest, at the tropopause, 150 hectopascals, subtropical westerly jets, there's some maybe 3 meters per second stronger. The most notable season is probably March, April, May. Look at that. Also, this one's really, I didn't expect this. So this says that during QBO westerlies, in the uppermost troposphere in the eastern Pacific, the Walker circulation is 5 to 7 meters per second slower. This is another thing that nobody's pursued. It's another PhD. So the idea here would be, we know the Walker circulation is turning over like this, and we have Indonesian deep convection here. During QBO easterly, the tropopause is higher, the convection is demonstrably greater. Colin Moore and Lee Martin and I did paper work. We showed that highly reflective cloud and outgoing long-wave radiation also follow these patterns of deep convection in the QBO modulation of them. So if you reduce convection over Indonesia, the Walker circulation weakens, so the eastward flow is reduced. In March, April, May, why? Okay, so this is just a zoom in on that, showing this deficit of the westerly flow. And this is interesting because this is a waveguide for velocity wave energy often. If there's westerlies here, they can get into the southern hemisphere. But during March, April, May, during QBO westerlies, maybe they can't. One other comment before going to the last result is, if you see that this is just 150 hectopascal winds, so here's the westerly jets in the subtropics, and there's easterly flow where there's convection, because thunderstorms create easterlies upward to the upper troposphere, is an educated guess. I don't know if that's true for an explanation. Maybe you could also think of convective heating will create a gyre and easterly flow on the equatorward side of it. That's another aspect of this problem. But what I want to point out is, if you make this flow more easterly in the upper troposphere during QBO westerly, and then you have QBO westerly in the stratosphere, that increases the shear. QBO westerly winds increase the shear from 150 to 70 in the tropics, especially near convective regions. And the reason why I point that out is I was hoping to use the seasonal geographical patterns to tease out, to try to separate the two hypotheses, that it's the thermal anomalies rather than the wind shear that's influencing subtropical and tropical convection. Okay, the last result, this may be the most long-lasting, but surely people will try to calculate these and update them. Here's a temperature pattern, and it just shows the altitude and latitudinal integration. If you take a snapshot of a QBO, let's say a warm temperature anomaly with descending QBO westerlies, this is the zonal wind corresponding plot, we can see that there's descent, and order of magnitude is less than a millimeter per second. We can see convergence here, and that's on the order of tens of centimeters per second. And overall, what we see is a nine-element checkerboard pattern, or tic-tac-toe pattern. So if you know that you have a warm anomaly here, it's 99% likely that you're going to have a cold anomaly all the way along the extratropical tropopause. So then if you calculate dt dy and build up du dz, then we can understand why you have a westerly wind maximum associated in the subtropical westerly jet regime with QBO westerly. See this horseshoe-shaped structure. If you go at 50 hectopascals over to here, you get into a node. There's not much signal. And so you can't, if you just look at one level, really appreciate this simple structure in 2D. I'd also like to point out this is statistically significant easterly anomaly during QBO westerly in the troposphere. I think it's the zonal averaging of the reduction of the Walker circulation. And then you can look at each season, and this confirms previous work which has shown that, well, these are the temperature plots, so you can see sort of 9 elements, a tic-tac-toe pattern for each. December, January, February, the winter's on this side. These thermal anomalies are really amplified on the winter side. Let's see here. Oh, June, July, August, yes, the thermal anomalies in the circulation are amplified on the winter side. So I mentioned before, Dunkerton and Kinnersley and few other people have been studying how the QBO interacts with extratropical wave driving in order to cause this asymmetry. All right, so some results from considering these observations. The QBO mean meridional circulation modulates the UTLS with antiphasing between the tropics and subtropics. So it's a very nice altitude and latitude integrated concept. The range across the QBO for tropical tropopause is about 0.5 to 2K, or 100 to 300 meters, or 1 to 3 hectopascals, being colder and higher in the tropics during QBO easterly. And this is especially true during boreal winter and spring. The QBO temperature signal tends to be larger in regions where deep convection is common. And I really would like to hear some of you are really knowledgeable about cloud dynamics. I want you to tell me why that happens. The QBO signal in the southern subtropics is enhanced during austral winter. It's a big effect, and also March, April, May. And then during QBO westerly, the subtropical westerly jet is enhanced, while the Walker circulation is weaker, especially during boreal spring. And then also this is the first quantitative climatology of the mean meridional circulation. So this was, I actually gave a talk on this in 2000, and that was one of the slides. This is before PowerPoint, almost. I hadn't used PowerPoint at that point. It was fun, you can draw little pictures on acetate and type up stuff and run it through a Xerox machine. Very like it. Nostalgia, right? Okay, so one theory can be called the temperature effect or the static stability effect. If you put a cold anomaly on top of a deep cloud, won't it get a little higher? It seems like it would. And so that ties in a little bit with what Reed and Gage talked about it. Emmanuel has these ideas of generalized convection. One element, a tropical cyclone, a mesial convective complex, you name it, it's going to have more thermodynamic efficiency. The tropopause is colder and higher because they have a difference in temperature that's greater. This is making use of the somewhat loose analogy with the Carnot energy cycle. Probably something to it. And the other idea, which actually had more adherents, starting with Bill Gray in '68, all these people talked about, well, if you have stronger wind shear, isn't it just going to kind of discombobulate the cloud at the top, and it won't be coherent. It's not going to grow as well. So if you can reduce wind shear, then maybe the clouds will grow better. And then we tossed in this third hat into the ring based on, I guess it was Robert Merrill originally thought of this, but I know Greg has done some work on it, which is there's greater outflow, ease of outflow if the inertial stability in the environment in the upper troposphere is weaker, and that maybe can help thunderstorms grow better. In making maps of inertial stability, or just zeta times F plus zeta, it didn't seem to correlate all that well with the temperature anomalies that we see. So it's probably a combination of 1 and 2. I really like Marco Giorgetta's numerical study from the late 90s. He imposed QBO anomalies in the FM4 model and found this correlation that you get more tropical cloudiness in Indonesia if you can have a cooler tropopause, or if you can reduce the shear in the UTLS. And maybe they go hand in hand. So here's a possible interpretation. I'm just trying to make guesses about the physics, underlying physics. First of all, we know that the vertical motions associated with the MMC alter temperature structure across 40 south to 40 north. And there's a regional enhancement of the signal associated with the dynamics of deep convection. Now, this part. Both the static stability hypothesis and wind shear hypothesis are supported by the observed geographical and seasonal variations. That is, where there's deep convection, like Indonesia, the QBO temperature range is large. That's also where you have an anomalous 150 hectopascal easterly flow, which means the QBO can manipulate that, and QBO easterly diminishes the shear in those regions. So they're temporally and geographically correlated. Both effects probably are contributing. And then the last part, in the last few years, this has become really fun to see. The modulation of the UTLS by the QBO can interact with ENSO. We can argue on and on which way the cause and effect goes there. They're both long-term phenomena. It's probably synergistically drifting together. Big effect on the MJO. During QBO easterly, an MJO will amplify and stall in about whatever phase 4 perhaps. In Indonesia, I don't know if that's the right number. So amplification makes sense with a deeper class, but why it would stall? A more nonlinear aspect, I guess. And then this also is quite a few papers being written lately on Atlantic and, for example, Atlantic and Pacific differences in the QBO modulation of the subtropical westerly jet through radiation of planetary waves. So it's been a fun exploration, and I'm glad everything turned out well. And thank you for listening.
Okay, so we've gone a little bit over time, so we're just going to take 1 or 2 questions, and then whoever else has extra questions can stick around afterwards, assuming Matt has time. Are there any student questions? I'm going to preferentially go for a student question. Evan.
You mentioned early on that the QBO doesn't modulate with like seasons or with the yearly cycle, that it's kind of fixed, and that's kind of a weird thing. So my question is, what would it modulate with? Like, does it go with planet diameter or like atmosphere density? I'm just trying to understand.
Yeah. So just to clarify that one statement, the QBO descends more quickly during northern spring, and so there tends to be a kind of a splitting of the period of the QBO into 2 bins because of that. That's been studied by a few people. But generally, it's still a true statement, I think, that the QBO period is, to first order, independent of the annual cycle going around the sun. Tim Dunkerton has done some numerical experiments where it has bursts of noisy waves or protracted wave forcing and tried to study the effects on the period of the QBO. I think that if you have more collective thunderstorms and wave forcing, that the QBO period slowly reduces. I think that might be the result there. Peter Haynes has been studying from kind of fundamental theoretical points of view what ought to be the meridional extent based on really fundamental assumptions. So theoreticians are trying to consider that, but a lot of this, I think, has room for improvement and understanding.
Okay, we'll take one more quick question. Greg?
The tropical easterly jet is very high in the tropics, and it seems that it moves eastward from the South Asian monsoon or westward. And so the question is, I seem to think, I get the impression that when there's an easterly QBO like this year, that the movement of the tropical easterly jet from South Asia into the Atlantic seems to be more robust. Do you have any indication?
I always lose track of the QBO. I don't know what phase it is. So it's easterly right now? All right. I think the autocorrelation goes down to 0.5 after 7 months, so I tend to lose track of it. QBO easterly, and you say a stronger
pulse
that will be
toward
consistent
the
with
west.
more convective forcing of the whole jar and a stronger westward flow.
Yeah, well, there's some theories, as we've talked about before, that the movement of the tropical easterly jet into the Atlantic enhances the tropical cyclone season. and it seems to be more of a robust movement.
Because they can get toward North America faster?
Well, there's less shear with the QBO.
Okay.
The QBO is eastern.
Yeah, I've got some pictures if you want to talk about tropical cyclones. I think Bill Gray was right in Oregon. Who knows?
Okay, since we're over time, I think we're going to call it there. If anyone else has any additional questions,